Imagine for a second, you're trying to find the perfect combination to this massive, heavy steel safe.
Right.
You are a master locksmith. You're turning the dials, listening for the clicks. But here's the catch. Every single time you guess wrong, the safe actually multiplies in size.
It just gets bigger and bigger.
Exactly. Welcome to the deep dive. Our mission today is unpacking a highly technical, but honestly incredibly fascinating piece of engineering documentation.
Yeah, it really is a wild read.
It is. It's a 2026 paper by a developer known as Luck036, and it is titled Get Ready for This Multi-Level K-Way Circuit Partitioning via Middle Levels Gray Code.
I know the title is, it's pretty dense.
Extremely dense.
But the stakes here, they're universally relatable to anyone who works with complex systems. This source is fundamentally about the pursuit of something called global optimality.
Global optimality.
Yeah, which basically means finding not just a functional way to organize a massive chaotic system, but like the mathematically perfect, undeniable, absolute best way to do it.
No compromises.
Exactly. And the tension in this document, what makes it so fascinating, comes from the heavy, gritty software engineering required to pull that pure math out of the theoretical realm.
Right, because math on paper is perfect.
It is. But you have to force it to run on physical hardware without, literally melting the computer down.
Okay, let's unpack this for you. To really wrap your head around what this developer is trying to achieve, we need to look at how engineers design complex circuits in the first place.
Yeah, let's lay the groundwork.
When you have billions of microscopic components inside a modern CPU, they all have to communicate, right? You have to group them efficiently.
Which is a process called partitioning.
Right, partitioning. And we're dealing with two main concepts here that you'll hear us mention, a netlist and modules.
Right.
You can think of modules as the actual physical pieces of the chip. They are like the little microscopic calculation factories doing all the actual math.
Oh, data factories.
Yeah, exactly. And the netlist is basically the giant tangled master blueprint of wires casting all those tiny factories together.
And we should probably clarify the specific type of blueprint we are looking at here, because it's not simple. In modern circuit design, we are working with something called a hypergraph.
A hypergraph. Okay. How is that different from a normal graph?
Well, in a standard mathematical graph, a connection is like a tin can telephone string pulled tightly between two specific houses.
Okay, just point A directly connects to point B.
Exactly. But in a hypergraph, a net or a wire is much more like a massive group text message.
Oh, wow. Okay.
Yeah, so one single wire might connect to 50 different calculation factories at the exact same time.
That sounds chaotic.
It is. And partitioning is the act of trying to draw a border wall right through the middle of this sprawling metropolis.
Right.
You're trying to separate the modules into two distinct halves while cutting as few of those group text wires as physically possible.
Because, every single time you cut a wire, meaning a signal has to physically cross that border wall from one side of the chip all the way to the other. You introduce lag.
Yep, latency goes up.
You generate heat and, you consume a lot more power.
Exactly. Nobody wants a hot, slow, battery-draining phone.
No. But before we can talk about how this algorithm actually, builds that border wall for a massive metropolis, we really have to understand the mathematical engine running underneath the whole thing.
The core of it all.
Right. The source calls this the middle levels gray code. So how does this engine actually work in practice?
Well, let's try to visualize the mechanics. The system represents the modules using bit strings.
So just sequences of ones and zeros?
Exactly, just ones and zeros. If a module is assigned a 1, it lives on the left side of our border wall.
Okay.
And if it gets a 0, it lives on the right side. Now, the algorithm operates using a very specific bit string length, which is defined by the formula L equals 2n plus 1.
2n plus 1. Wait, so 2 times any number is even, plus 1 makes it odd, meaning the length of the string is literally always an odd number.
That is correct. It is always odd.
Why?
The algorithm artificially forces an odd length so it can focus entirely on the middle levels of all possible combinations.
Middle levels.
Yeah. Out of all the millions of ways you could arrange those ones and zeros, it deliberately only visits patterns that have a weight of n or n plus 1.
Okay, you lost me a bit. What does weight mean in this context?
Oh, right. In plain terms, weight just means the total number of ones in the string.
Ah, okay, just counting the ones.
Right. So by forcing the weight to be n or n plus 1, the algorithm ensures it is only ever looking at almost perfectly balanced splits.
So roughly half the modules are on the left and half are on the right.
Exactly. A perfectly fair division.
I was trying to picture this for you listening, and I just keep coming back to our locksmith from the beginning.
The guy cracking the safe.
Yeah, trying to crack the safe. If I'm an amateur trying to open a combination lock, I might, I don't know, spin all the dials wildly.
Just guessing.
Right. I'll try a few birthdays, get frustrated, spin them again, and I will inevitably end up checking the exact same wrong combinations over and over again without even realizing it.
Yeah, you're just wasting time, which honestly is exactly how a lot of basic algorithms approach massive sorting problems.
Surely.
Yeah, they randomize, they shake things up, and they just hope for the best.
But the gray code algorithm is not doing that. It is the absolute master locksmith. Because of the way the math is structured, to move from one pattern to the next, the algorithm flips exactly one single bit at a time.
Just one.
It methodically turns exactly one dial on the safe, one single click,
Yeah.
just one module moving
Oh.
across the border wall at a time. And by doing this with, perfect mathematical discipline, the algorithm absolutely guarantees that it maps out every single perfectly balanced combination without ever retracing its steps.
What's fascinating here is how perfectly that abstract mathematical concept mirrors a very gritty standard technique in physical circuit partitioning.
Oh, yeah. How so?
It mirrors what's called an FM move.
FM.
Yeah, named after the Fiducia-Mathesi's algorithm. An FN move is quite literally the physical act of moving one module to the other side of the partition block to see if it improves the overall wire cut cost.
Oh, I see.
So by flipping exactly one bit per step, the middle level's gray code guarantees that absolutely every balanced two-way partition is visited.
You leave no stone unturned.
Exactly. You achieve true global optimality.
And this is but earlier we mentioned that the safe multiplies in size every time you guess.
It does. And the scalability numbers provided in the developer's source documentation are honestly staggering.
I was shocked reading them.
Right. Because if you only have 11 modules to sort, the gray code engine has to check 924 different states.
Which sounds like a lot.
It does. But a computer rips through that in under 1 millisecond.
Oh, wow. So it's blisteringly fast.
For 11 modules, yes. But the problem arises when we increase the load to just 25 modules.
And 25 modules is nothing. I mean, in the grand scheme of a computer chip with literally billions of transistors, 25 is a microscopic speck.
A speck of dust.
Yeah. Yet, for just 25 modules, the number of states it has to check explodes to 10.4 million.
10.4 million.
And the time jumps from a fraction of a millisecond to 3.4 seconds.
Yeah. That is the brutal, unforgiving reality of exponential growth. And it sets up the entire central conflict of the developer's documentation.
Right.
Because you have this elegant, beautiful gray code that guarantees mathematically perfect optimization. But it physically cannot handle more than 25 modules.
It hits a wall.
A huge wall. If you try to feed it 100 modules, the heat death of the universe would arrive before the calculation finished.
That's terrifying. So how do they actually use this thing?
Well, to survive this, the system has to contract the problem first.
Contract it.
Yeah. It takes thousands of individual modules, and it squishes them together, clustering them into super modules.
Oh, okay.
And it keeps squishing until there are fewer than 25 super pieces left.
Ah, so then they can use the gray code.
Exactly. Then it unleashes the perfect gray code math to sort those 25 giant pieces, and finally it extends the whole thing back out to its original size.
Okay, but that transition point, moving from the pure, pristine world of theoretical mathematics into the, messy physical reality of C++ code and contraction loops, that is where the bugs start crawling out of the woodwork.
Big time.
Yeah, the developer dedicated a whole section to the bug hunt, and it is just a fantastic look under the hood of software engineering. It really highlights how fragile these systems can be, Let's look at the first major failure. They detail a catastrophic stack overflow on a benchmark known as IBM A01.
IBM A01. So
Not-
what was that exactly?
It was a test circuit with 12,752 modules and 50,000 hypergraph nets.
Okay, so massive. It's huge. And the developer tried to run the multi-level contraction clustering we just discussed, and the entire system completely collapsed, just died.
Wait, okay. If it's hitting a stack overflow, why didn't the system just stop? I mean, was it blindly following a loop without any kind of failsafe?
Pretty much, yeah.
Because I read this part and I immediately thought of trying to zip a computer file.
Oh, that's a good comparison.
Right. If you zip a massive text document, it shrinks beautifully. The compression algorithm does its job.
Yeah.
But if you try to zip an MP4 video file, something that is honestly already highly compressed, The new zip file is basically the exact same size as the original.
Exactly.
So, was the algorithm just blindly trying to compress an uncompressible file?
That is a phenomenal analogy, and it's
Yes.
exactly what was happening here. Normally, each clustering pass reduces the size of the graph by about 60%.
Okay, 60% is a solid chunk.
It is. But on this specific IBM01 circuit, the internal geometry was pathological. As the graph shrank, the contraction ratio just degraded terribly.
Oh,
Yeah, instead of shrinking by 60%, it dropped down to a useless 4%.
4%. That's nothing.
Nothing. But the mathematical theory assumes the graph will always shrink smoothly, so the code lacked a reality check.
Oh, I see.
It kept calling itself,
Hmm.
digging deeper and deeper into a recursive loop, just exhausting the computer's stack memory, trying to shrink a graph that was absolutely refusing to shrink.
Eh,
It dove 14 levels deep until the program just died.
14 level. Wow. So they needed to build like a sensor for our digital zipper.
Exactly.
If the file is only shrinking by a few kilobytes, the system needs the autonomy to just say, okay, that's enough. We are stopping here.
Which is the pragmatic fix the developer eventually implemented. They added a strict contraction ratio guard.
A guard. How did that work?
They wrote a hard mathematical rule into the code. It basically said only recurse into another clustering loop if the newly contracted graph is significantly smaller than the original.
Define significantly.
Specifically, the size of the contracted graph multiplied by 1.5 must be strictly less than the original size.
Okay.
And that one simple guardrail capped the recursion levels for IBM01 from 14 down to about 3. It instantly cured the stack overflow.
It's amazing how one line of code stops a total system collapse.
It really is.
But the bug hunt didn't end there, right? Because there is a section detailing something called the half bits formula that just perfectly illustrates how one tiny mathematical typo can bring a supercomputer to its knees.
Oh, man, yeah. This raises such an important question about how engineers translate pure math into functional code.
Right.
Because remember earlier, we said the gray code strictly requires the bit string length to be an odd number. L equals 2n plus 1.
Yep. Has to be odd.
Well, real-world circuits don't always conveniently have an odd number of modules.
Naturally.
So to handle an even number of modules, the system has to artificially add a dummy bit to force the lengths to be odd.
Okay, that makes sense. And to calculate how many bits they needed, the original C code used a mathematical ceiling method.
Right.
So the formula was basically n plus 1 divided by 2. If n is 9, 9 plus 1 is 10 divided by 2 is 5.
Perfectly logical.
Seems completely hard.
Harmless until you look closely at the math for odd numbers. That ceiling formula accidentally added 2 extra dummy bits whenever n was already an odd number.
2 extra bits, which, I mean, in normal day-to-day software, 2 extra bits of data is nothing. It's barely a rounding error.
In a linear system, yes, absolutely nothing. But we are operating in an exponential space here.
Oh, right.
Every single extra bit massively inflates the size of the safe you were trying to crack.
Wow.
Because of those 2 accidental dummy bits, millions of extra, utterly useless combinations were being calculated by a gray code engine for absolutely no reason.
Just grind in the gears. So the developer swapped the ceiling method for a simple floor method.
Just n divided by 2.
Just n divided by 2. That was the entire fix.
One minor adjustment. And the result was absolutely staggering. The time it took to search the 25 module benchmark dropped from 12.9 seconds all the way down to 3.4 seconds.
Wait, really?
Yeah. That is a massive 3.8 times speed up across the entire software architecture, just by stopping the engine from calculating ghosts.
That is wild. We also need to talk about memory safety, though, because moving this old C-style codebase into modern C++ compilers created a whole new set of hazards.
It did. The original implementation used something called variable length arrays, or VLAs.
Right. What's the issue with the VLAs?
Well, VLAs allocate their memory directly on the stack. They are incredibly fast, but they're very rigid. They claim a specific chunk of memory, and they never reallocate or move.
Okay.
But when adapting this engine to Microsoft's C++ compiler, which doesn't support VLAs in the same way, the developer had to replace them with a dynamic structure called standard vector.
Okay, so why are dynamic vectors dangerous in a highly recursive system like this?
To understand why, you have to look at how a vector physically manages memory behind the scenes. Think of a vector like a wooden bookshelf.
A bookshelf, all right.
You have 5 books on a shelf that holds exactly 5 books. Now, you want to add a 6th book.
You can't just shove it in.
Exactly.
Hmm.
The vector requires a single continuous block of physical space. So the computer actually has to pack up all 5 books, physically walk them down the hall to a larger empty shelf in your RAM, unpack them, and then add the 6th book.
Which takes time, obviously.
Right.
But more importantly, if any other part of the program had a map pointing to the location of the old shelf, they are now just pointing at an empty wall.
That is exactly the problem. Any pointers looking at the old memory location suddenly point to garbage data.
And when the program tries to read that garbage data,
Crash. You get a catastrophic segmentation fault.
ouch.
Yeah. To survive this, the developer had to implement a masterclass in defensive programming. They rigorously used functions like reserve to pre-allocate the exact massive memory sizes they knew the bookshelf would eventually need.
Oh, so building a massive shelf from day one?
Exactly, preventing it from ever having to move down the hall in the first place. And they used emplaceback to safely construct elements directly in their final resting place.
Okay, so we spent all this time exploring how they achieved absolute perfection for dividing a circuit into two halves, right? They stopped the stack overflows, they fixed the dummy bits, they secured the memory arrays.
Yeah, a lot of work for 2 halves.
Right. But a modern CPU isn't just a duplex separated by one wall. It is a massive metropolis.
Very true.
You have to divide it into dozens of microregions. So does our perfect but kind of fragile two-way math just shatter when you try to split it into 6 or 8 or 16 pieces.
It absolutely would shatter if you approached it naively. But this is where the architecture of the new mid-LVL-KWay part MEGCR system really shines.
Another catchy name.
I know, engineers love their acronyms. But the developer needed to transition from two-way partitioning to K-way partitioning. K basically just being the variable for however many pieces you want.
Okay, K-way.
Right. And the key insight from the documentation is how they handled the global blueprint during this. Because you might assume that to divide a small section of a massive circuit, you would extract a tiny subnet list.
Like a miniature copy?
Yeah, a miniature copy of just the wires in the specific neighborhood you're looking at.
I mean, that seems like common sense. Give the algorithm a smaller piece of paper to work on so it doesn't just get overwhelmed.
It seems logical, but it is fundamentally flawed for K-way partitioning.
Why?
If you only look at the miniature copy of the neighborhood, you lose all visibility of how those local modules connect to the rest of the giant metropolis.
Oh.
If you cut a wire in the subnet list, you might accidentally be severing a massive critical group text wire that actually spans the whole chip.
Oh, wow. I didn't think of that. So you cause chaos elsewhere.
Exactly. So to solve this, the new algorithm operates on the full net list at all times.
The whole thing.
The whole thing. It uses a really clever bit-module mapping. The gray code engine just does its thing flipping generic bits, zeros and ones.
Right.
But the mapping translates that generic bit position into the exact physical index of the module in the massive master blueprint.
Oh.
So the system remains perfectly aware of the global consequences of every tiny local move it makes.
That's brilliant. But we established earlier that the absolute limit for the perfect gray code search is 25 modules before the math just takes years to finish.
We did.
How do you map a 6-way split without the computer melting down?
So the developer derived a specific scaling limit formula for K-way partitions. The formula is 25 times K divided by 2.
Okay, let's walk through my 6-way example.
Sure.
If K is 6, the formula dictates an absolute limit of 75 modules.
Correct.
Hold on. 75 modules. The exponential curve we talked about earlier means 25 modules takes 3.4 seconds. 75 modules should literally take longer than the universe has existed. How is the system handling a 75 module limit without freezing?
It sounds impossible, but if we connect this to the bigger picture, it doesn't freeze because of a strategy called pairwise refinement.
Pairwise refinement.
Yeah. The math behind the K-way formula is based on combinations. The algorithm doesn't try to solve all 6 regions of the metropolis simultaneously. It pairs them off. It pits region 1 against region 2, then region 1 against region 3, then region 2 against region 4. It essentially runs a round-robin tournament.
Ah, okay. So it breaks the giant problem into a series of head-to-head matchups?
Precisely.
Mm.
If you have 6 partitions, there are exactly 15 possible unique pairings in a round-robin tournament.
Got it.
The 75 total allowed modules are dynamically distributed across those 15 pairs. That means each specific pair only sees an average of about 5 modules that actually need sorting.
Oh. And the gray code engine chews through 5 modules in a microsecond.
Exactly. And if any specific head-to-head pair happens to contain more than 15 overlapping modules, the algorithm recognizes the mathematical danger and simply skips them to preserve the system's speed.
Wow.
It's a highly elegant mathematical compromise.
Here's where it gets really interesting for you listening. Let me make sure I'm wrapping my head around this whole multi level strategy.
Go for it.
Instead of trying to solve the massive billion piece puzzle all at once, the algorithm squishes the tiny pieces into big, manageable chunks. That's the contraction phase.
Yep.
Then it isolates tiny, critical pockets of those chunks. It perfectly solves those little isolated mini puzzles at the very bottom using the gray code locksmith technique we talked about.
That's right.
And finally, it blows the whole thing back up to full size, kind of smoothing out the edges of the border walls.
That is the complete architecture. They actually call that final smoothing phase legalization.
Legalization.
Yeah. And the documentation provides the concrete results of this massive undertaking. The developer reports that 68 exhaustive integration tests passed across both Windows and macOS compilers.
Oh, nice.
Yeah. It successfully conquered industry standard benchmark circuits from IBM P1 and Yosis.
So all that defensive programming, the memory vector protection, the contraction guards, it actually all paid off.
It did. And there is also a specific design rationale in the source that highlights why the multi-level strategy works so effectively.
Which is?
The developer deliberately configured the system to run the exhaustive leaf check, the perfect gray code math, before the final legalization smoothing phase.
Why does the order matter?
By executing the steps in that specific order, they absolutely guarantee that the exhaustive search gets to visit all the balanced partitions without being artificially blocked by premature rules. It prioritizes perfect mathematical exploration over immediate conformity.
But even a masterpiece has limitations, right? The documentation lists several areas for future work where the system still struggles.
Yes. The developer is very transparent about the walls they couldn't break.
I appreciate that.
The most obvious limitation is that the core engine remains strictly exponential. It will only ever be feasible for fewer than 25 modules in a two-way split.
You simply cannot defeat the cold mathematics of exponential combinations.
You really can't. They also detail a severe bottleneck with the netless scanning.
Oh, scanning the wires.
Right. Every single time the gray code locksmith turns the dial one click, every time one module moves across the wall, the system has to manually scan all the connecting wires of that specific module to see if the group text was severed.
And when you are checking millions of states.
You are performing millions of full wire scans.
Which is incredibly heavy on the CPU.
Very. They suggest that future versions could maybe pre-compute those wire gains to speed things up. But honestly, the most fascinating limitation they noted circles back to that IBM 01 benchmark we discussed earlier.
Oh, the one that caused the massive stack overflow.
Yeah. Where they had to implement the contraction ratio guard because the file just wouldn't shrink.
Right.
Even after they fixed the crash, they noticed something highly paradoxical about the quality of the final blueprint.
Paradoxical how?
When they ran the partitioner without any contraction, just a raw, flat pass on the original data, the final wire cut cost score was 564. And in this context, a lower score is better.
Okay, so baseline score of 564.
But when they used the fancy multi-level contraction clustering to shrink the problem first,
Let me guess, the final cost actually degraded.
it did. The score jumped to 786.
That is a staggering irony.
Right.
The very mechanism designed to make the massive problem small enough to solve perfectly actually made the final global answer worse.
It's wild.
How does that even happen?
Well, it happens because algorithms make assumptions. Contraction assumes that if modules are tightly wired together at the microscopic level, they should permanently stay together at the macroscopic level.
That sounds reasonable.
It does, but sometimes forcing that rigid local grouping traps you in a bad global configuration. You force a local neighborhood to stay together, but doing so forces you to cut a massive highway that spans the whole city.
You missed the forest for the trees.
Exactly.
So what does this all mean? We have gone from the abstract theoretical mathematics of L equals 2 n plus 1 bit strings to physical memory allocation vectors to stack overflows absolutely destroying compilers.
It's quite a journey.
It is. At its heart, this document is just a beautiful collision between pure theory and gritty physical reality. You have the middle level's gray code, which is mathematically pristine.
Perfect on paper.
Right, and then you have the software engineer armed with contraction guards and floor formulas, desperately trying to bolt that perfect math onto a physical machine that has hard limits.
And that tension is deeply relevant to anyone dealing with massive amounts of data in their own field. You have to understand that true perfection, global optimality is often only achievable in tiny, highly isolated pockets.
Mm.
If you want to scale up and tackle the whole messy world, you cannot rely purely on brute force perfection. You have to rely on heuristics, compromises, and approximations.
You have to accept some mess.
Exactly. Sometimes you just need the wisdom to know when to stop compressing the file. You have to recognize when forcing a system to contract is actually hurting your final result more than it's helping.
It is a profound balancing act. And thinking about balance brings up one final detail from the source that I keep coming back to.
What's that?
The entire core algorithm is built on the strict assumption that the partitions must be exactly balanced. Weight n or weight n plus 1.
Right. A perfectly even 50-50 split of the chip.
Right. Mathematical symmetry is literally the foundation of the gray code logic.
It absolutely is.
But look around at nature. Look at organically optimized human systems like city traffic grids, supply chains, or even how our own brains partition tasks.
They're messy.
They are almost never perfectly symmetrical. Slight imbalances, putting a little more weight on one side than the other, often yield radically greater overall efficiency.
Well, that's an interesting point.
It makes you wonder, if an algorithm is forcing perfect mathematical symmetry at the micro level by its very design, could it be artificially blinding us to much better, wonderfully asymmetrical solutions at the macro level?
Mm.
Is our obsession with mathematical balance actually holding us back? Something for you to think about next time you try to split things perfectly down the middle.